Have you ever wondered why power engineers spend so much time talking about reactive power? A type of power that, by definition, does no useful work. It does not turn motors, it does not light lamps, and yet entire research fields, grid codes, and control strategies are built around it. So here is the real question. Why does something called non-active power play such an active role in keeping the lights on? In this episode, we will uncover the hidden story of reactive power, from its physical origins to its critical role in modern power systems, renewable energy integration, and grid stability. To understand reactive power, we must go back to the basics. In AC systems, electrical power is not a single quantity. It is divided into three fundamental components: active power, P, reactive power, Q, and apparent power, S. Active power is what everyone understands. It is the power that produces motion, light, and heat. It is measured in watts. It is billed. Reactive power, however, is different. It exists because real power systems are not purely resistive. They contain inductance and capacitance. And this is where the story begins. Reactive power is not imaginary. It is not a mathematical trick. It represents real energy exchange between the grid and electromagnetic fields. Inductors store energy in magnetic fields. Capacitors store energy in electric fields. Every AC cycle, energy is borrowed from the source and then returned. No net consumption, but continuous interaction. Without this interaction, motors cannot produce torque, transformers cannot operate, and transmission lines cannot function properly. Reactive power is the price we pay for operating AC systems. One of the most important rules in power system engineering is this: active power mainly controls frequency, and reactive power mainly controls voltage. When reactive power is insufficient, voltage drops. When it is excessive, voltage rises. This is not a coincidence. It is deeply rooted in the physics of AC networks. Voltage instability is, at its core, a reactive power problem. Imagine a heavily loaded power system. Demand increases. Reactive power demand increases faster than active power demand. Voltage starts to fall. Lower voltage causes higher currents. Higher currents increase reactive power consumption. This creates a dangerous feedback loop. If reactive support is not available locally, the system collapses. Many historical blackouts followed exactly this pattern. Unlike active power, reactive power does not travel well. Trying to transmit reactive power over long distances leads to high losses, large voltage drops, and inefficient operation. That is why reactive power must be generated close to where it is consumed. This explains the widespread use of capacitor banks, synchronous condensers, and SVCs and STATCOMs. Reactive power is a local service. Modern power systems are changing. Wind and solar generators are connected through power electronics. These converters can inject reactive power very fast, can support voltage during faults, and are required by grid codes to provide reactive support. Even at zero active power, reactive power has become a grid stability tool, not just a side effect. Protection systems rely heavily on voltage measurements. Reactive power directly affects distance protection, voltage-based relays, and converter fault ride-through behavior. In modern FACS and HVDC systems, reactive current injection is often the first control action during faults. Now, the research trend makes sense. Improving reactive power compensation means better voltage stability, higher power transfer capability, reduced losses, and increased system resilience. Reactive power is not secondary. It is foundational. Calling reactive power non-active is misleading. It does not perform work, but it enables work. Without reactive power, active power cannot be delivered reliably. Reactive power is invisible, but it is essential. If you want to understand modern power systems, HVDC grids, renewable integration, FACS devices, and advanced control strategies, you must understand reactive power. It is the silent force holding the grid together. Thanks for watching. Stay safe and stay curious.